Hi everyone. Today we'll be discuss two main questions. First, what did we do to improve the performance of our regression? Second, what did we do to access and improve the fit of our regression? We will talk through our process step by step, showing how we move from basic model to stronger, more stable final model. And the first part is what we did to improve the performance of our regressor. When we first approached this regression problem, our goal was not just to build one model, but to progressively improve performance through better pre-processing, smarter modeling choices, and systematic tuning, transforming the target variable. One of our first and most impactful decision we made was applying a log transformation to target variable, sell price. Housing prices are typical right-scaled, meaning there are few extremely expensive houses that stretch the distribution. This scaleness can negatively impact a regression model because they tend to over reformize large errors. By applying a log transformation, we reduce skewness, stabilize variance, and made the distribution closer to normal. This helped the model learn proportional relationships rather than being dominated by extreme values. As a result, we improve prediction stability and reduce overall errors. And the second part is handling missing value strategically. Instead of dropping rows with missing values, which will reduce our dataset size, we carefully handle missing data. For numerical features, we filled missing value using the median. The median is robust but outlier and work well for skewness data. For categorical variables, we filled missing values with either none or most frequent category depending on the feature context. This approach preserves information and prevent the model from learning biases pattern due to the missingness. Encoding category variable property. Because many features were categorical, we apply one-hot encoding to convert them into numerical format. Later, we improved this by setting parameters such as handling unknown categories and filtering rare categories. This reduced noise caused by infrequent value and helped improve generalizations. Proper encoding ensured that the model could effectively capture meaningful difference between categories without overfitting to rather observations. We did not rely on single algorithm. Instead, we test multiple models and compared their performance. The first model we use is random forest. We start with random forest model to establish a stronger baseline. Random forest is robust and handles nonlinear relationships well. It gives us a reasonable starting performance. However, we noticed that boosting method might capture pattern more efficiently. Next, we implement CharVG boosting with cross validation. We use a relatively small learning rate and large number of estimators. The small learning rate allowed the model to learn gradually, reducing the risk of overfitting. We also apply subsampling and column sampling to reduce variance. With five-fold cross-validation, we observe a mean RMSE around 0.124 on the log scale, which improve over the baseline model. We then transitioned to light GBM, which is optimized for efficiency and often perform very well on structured stable data. We turn several hyperparameter, including learning rate, number of leaves, subsample ratio, column sample ratio, L1 and L2 regularization. We also implement early stopping. This allowed training to stop automatically once validation performance stopped improving. This prevented overfitting and selected the optimal number for boosting rounds. This model further improves stability and performance. Finally, we implement model blending. We combined 80% of light GBM and 20% of radius regression. Light GBM capture nonlinear interactions effectively, while radius regression capture linear relationships and add regularizations. By blending them, we reduce variance and balance bias. The blend model achieved the best across validation RMSE around 0.1 to 3, slightly outperforming in individual models. This confirmed that combining complement models improve performance. And my group mate will explain the part two.
Okay, for the part two is how we assess that and improve model fit. Improving performance alone is not enough. We also needed to ensure that the model generalized well and did not overfit. So the first one is key-fold cross-validation. Instead of using a single train validation split, we use five-fold cross-validation. This approach allowed us to evaluate performance across multiple subsets, measure stability, reduce randomness in validation scores. By examining fold by fold RMSE, we could assess whether the model was consistent or unstable. And second is monitoring RMSE. We use root mean squared error as our primary metric. Because we long transformed the target variable, we evaluated RMSE in long spaces. This aligns well with the computation metric and emphasizes proportional accuracy. Monitoring RMSE crossfolds allowed us to compare models objectively and choose the best performance one. And third one is early stopping. Early stopping played a critical role in improving fit. During the boosting, we monitor validation performance. If the validation error stopped improving for a set number of runs, training stopped automatically. This prevents the model from continuing to feed noise in the training data and helped us maintain generalization performance. And the fourth one is regularization. To reduce overfitting, we applied multiple regularization strategies, L1 and L2 potentials and subsplaining rows, column sampling, and controlling tree complexity. These techniques reduce model variance and improve generalization to thin data. And the fifth one is handling. We also filtered out extreme outliers by removing the top 1% of the target distribution. Extreme outliers can destroy the training and increase RMSE significantly. By removing them, we improved stability and achieved a more consistent cross-validation result. And finally, to summarize this, to improve the performance, we choose to launch transformers that target variable, handle the mixed data carefully, and encoded categorical variables properly. Turn the high hypermeters, switch it to Bayesian models, applied regularization, remove the extreme outliers, and use a model blending. And also to assess and improve the model fit, we choose to use a five-fold cross-validation, monitor RMSE constantly, applied early stopping, evaluated fold stability, compared multiple models, and balanced the bias and the variance. Overall, our approach was systematic and interactive. Rather than rely on a single model, we continuously improved the performance, learning validation strategy, and model combination. This structured process allow us to progressively reduce error and build a regressor that generalizes well and perform reliability. Yeah. Thank you guys for listening.